Okay. So let's slowly start the talks. У нас есть это для спикеров. Мы его презентацию здесь, да? Третьего у нас нет. Okay, guys, let's start. Please take a seat. Please take a seat. Everyone, we will have networking parts just right after the talks. Yes, moving to this direction. All right. Grab some drink, some food, and take a seat. Okay, we're live? Yeah? Hello everyone from the YouTube. And hello everyone at the audience. Really happy to see you here. It's been quite an intensive week. Have you been at the conference or the meetups yet? Yeah? Yeah, I see people are a bit exhausted. But let's get some, some energy kick for today, for today's meetup. We are discussing peer-to-peer networks today. And we have three amazing projects and three amazing speakers, co-founders, all three of them. So first will be Tom from Fluence Labs, and then followed by Joel from Ceramic, and then Alexis from Radicle. And then we will have networking and drinks. We have more food, we have desserts. So yeah, be active. We will have Q&A after each talk. And if you have any questions, there is no stupid question, remember. So any questions are welcome. Yeah, and let's welcome Tom, Tom Trowbridge, co-founder of Fluence Labs. Let's give a round of applause.
Great. Thank you, Anna. Anna is a core member of the team. I also think we should introduce the other members of the team that are here. We have Evgeny, we have Dimitri, and Bernard is back there, and then there's a core dev Folix somewhere hiding somewhere. There we go. So that's you got a lot of the core Fluence team here, which is great. So I want to talk about peer-to-peer and compute, and talk about the need for it, and why peer-to-peer matters, and why it matters particularly now. First, a quick background, a minute on Fluence. We're a peer-to-peer compute protocol. We're backed by some terrific investors. In fact, one of our investors from Polymorphic is in the audience, so great to see you. But and I'm a co-founder of Fluence, so you obviously heard my name. Don't go into that. But when you think peer-to-peer, what do you think of? I was going to ask the question, but I'm guessing most people would say Bitcoin. And Bitcoin being one of the first peer-to-peer kind of applications that we know. But the real application to popularize peer-to-peer and to make it mainstream to some extent was Napster back in 1999. And so I just think it's worth pushing this timeline of peer-to-peer, and actually even goes back to the late 70s, early 80s, where this architecture was discussed. But it goes back to kind of usage in 99. Unfortunately, Napster was shut down in 01, but we got Bitcoin in 2009. And Bitcoin is important because it solves a variety of peer-to-peer, of the issues that plague centralized systems, primarily censorship. And with Bitcoin, you would first time send value to somebody without an intermediary. And that was important from value perspective, but peer-to-peer can solve far greater problems, and there's far greater risks in the world than just value transfer. And so big tech is right now at the highest point of its kind of centralization and power we've seen. And so these are examples of several, censorship that I think people have seen, in particularly in Russia. It also happens in Venezuela and obviously in China, where big tech has to basically adhere to the directives of the totalitarian governments who want the narrative shaped a particular way. And that's something that we can see. You can see political opponents being censored. You can see stories being taken off, YouTube videos removed. And that's easy to do when you have a couple specific platforms that you can target that are the dominant platforms people use. But what's interesting, it's not only by totalitarian governments. We've seen it happen in the US. Some of it is explicit censorship, and some of it is sort of shadow censorship. But this is, the most, extreme example of this is in India, a very large democratic society that has censored and taken off protests or chat groups about protests, and even taken off opposing politicians and directed the management of applications to do so. And in a very kind of, meta discussion, they tried to have Twitter remove an article, to censor an article about censorship. So that's actually the level that some governments are going to, and democratic governments, to be clear. This is not just a Russia, a China issue. And now Twitter, to its credit, is suing the Indian government to prevent this type of censorship from standing. And so that is, I think, a very, but that's just worth keeping in mind. We may not see it every day. We may not think it affects us. But if this is happening around, and it is, and it's only increasing in terms of its prevalence. So why is this happening? It's, big tech has also a stranglehold on the web in terms of infrastructure. And so we've talked about the sort of applications that people use, but when you get into the infrastructure on which things are built, you also have an oligopolistic setup. And so you have the three dominant cloud providers that have at least 60% of the overall market, and they're growing revenue dramatically. And why are they doing that? Because you're effectively locked in to those networks. And when you join, it's super easy. They have a lot of services you can use. It allows you to get your applications and your product off the ground faster. But the bigger you get, the harder it is to leave. And there's a couple of examples of groups, I think it was Samsung, among others, who've left, but it's been incredibly expensive and hard to do. Years ago, Lyft was reported to be paying 14 cents a ride to AWS. That's probably a higher number now. And I mentioned the power they have. There is a social network with a couple million users that was knocked off with a couple days' notice for a terms of service violation. And this group is Parler, and I'm not sure Parler is something that we would, die on a hill for necessarily, but it just shows the power that the term of service can be an arbitrary on-off switch for any application. And as soon as they do that to Parler, all the other applications know that that is possible to happen to them as well. So that influences behavior additionally. So, and if they were really, incredibly resilient and never went down, some of these trade-offs might make sense. But frankly, the larger they get, the more complex those systems are, and the more prone to outages they are, and the bigger consequences those outages then have. And so this technology gets more and more complex as it scales. It's harder and harder to manage centrally, and more people use it, which means when something goes down, the impact is that much greater. So we've seen, WhatsApp and Facebook and others go down. AWS goes down, that's impacted us, maybe inconvenience here or there, but there are government agencies that run on some of these in some countries, and it can have a real-world impact when you can't communicate using the tools that you're accustomed to. And so this is not the internet we signed up for. You know, Tim Berners-Lee, the architect of the web, had a vision that everything was peer-to-peer, where everyone would be a publisher and everybody would be a consumer, and it would be a distributed web of easy-to-access information. And that hasn't worked because the internet rewards scale. And it's no fault necessarily of any of these companies, but the slightly bigger you get, the more you can invest in getting more users. The more users you have, the more you can monetize, the more you can advertise and get more users, and that cycle continues, so you naturally end up with monopolistic or oligopolistic setups. You have it in search, you have it in social media, you have it in hosting. That continues and the internet won't probably change unless we are successful in building a peer-to-peer alternative. And so, you know, how did we get here? We started off with mainframes and desktops, and that was companies, by and large, doing compute and doing kind of all the hosting themselves. In the kind of late 90s, the cloud started, and people started to be dragged, kicking and screaming, to the cloud. Everybody said, oh, I want to host it internally because it's cheaper, it's more resilient, et cetera. I want to control my data. Fast forward, and now the cloud is cheaper. The cloud is more resilient than people building and having their own IT staff and infrastructure in-house. And so the cloud has pulled away the mainframe and desktop world. But peer-to-peer platforms really are the next generation of this. And peer-to-peer is that next generation for three reasons. It's the next generation because it can scale better, it has higher security, and it's more resilient. And so those three attributes will drive peer-to-peer to be the future. It's not going to happen tomorrow, but that is the way we are headed. And frankly, we need to get in that direction. But let me talk about each of those: scalability, security, and resilience, one at a time. And so scalability. Open peer-to-peer can scale faster. When you have a global network of hardware, it can respond, and of software, they can respond to demand and price far faster than any centralized company. So when your global network is always able to scale, and the market can always scale faster than any individual entity when the right incentives are set up. And so you also can have more variability in terms of service and in terms of pricing when you have a network that is global. So the scalability for peer-to-peer, when mature, should be far more significant and far superior to any one centralized company. And with security, we're back to censorship resistance here. And when you have peer-to-peer applications running on peer-to-peer networks, you don't have single points of censorship. You don't have management to threaten to jail like you do in India. You don't have shareholders who are going to be upset if XYZ doesn't happen. You don't have boards who have reputations that are at risk. And so you have no legal entity to compel. And so when you have peer-to-peer applications running on peer-to-peer networks, you have a far more censorship resistant and a far more secure method of application design and of content delivery, which gets into resilience. Peer-to-peer doesn't have single points of failure. You have open source code, highly reviewable. Of course, code can have errors. It can in centralized systems as well, but open source, I think we can agree, has a much higher resiliency factor than closed source code. And peer-to-peer by nature is open source. You don't have centralized points of failure, and that leads to far more, and you have duplicative setups, both in terms of hardware and in terms of hosting. And so you end up with a far better solution from a secure perspective, from a security and resilience perspective. And where are we right now? We have payments, And so we were familiar with all of the payment systems out there that work from, Bitcoin to Ethereum, et cetera. I put Hedera on there. And also storage. Storage is also working very well right now. But what we don't have yet is decentralized compute. And when you put those three things together, you end up with a decentralized cloud, which is what we need. And so just a quick discussion on the traction payments, very well, right? Obviously, that number was 2 trillion not long ago, but it's still significant. And storage, Filecoin, Arweave, storage, all of these systems are functioning. They're headed in one direction in terms of growth, and that technology has largely solved peer-to-peer storage. But the compute is what we're all still working on. And the compute is, when we think of compute in peer-to-peer world, we often think of smart contracts. And smart contracts work, and that is peer-to-peer compute. The problem is it is slow and expensive. It is redundant, which is good, but it's constrained. And clearly there are a variety of layer twos working to reduce some of the cost and the scalability issues. But those obviously come with some level of security trade-offs depending on what it is. But on-chain compute currently cannot scale to the level of general purpose computation. You also have decentralized kind of hardware marketplaces, but those are designed for very specific applications, not designed, again, for general purpose. And so what you want to have something that doesn't have this high barrier to entry, i.e. high gas costs, and that effectively it's a function addressable and it's pluggable to blockchains, and you can run full featured application backends easily. That's what you should want in a peer-to-peer compute protocol. And that's what Fluence has, and others are doing it as well, where you can have any computation, and it's a function addressable and it's permissionless. So think of it as like a decentralized, Lambda function. And why do you want that? Well, one of those other reasons we talk about here is the deplatforming risk from Web 2. And this is just one example of Twitter. You can think of others as back to Farmville, et cetera, where if you really want to innovate, you should be able to take a DeFi example and build on top of existing applications and existing protocols. But in the Web 2 world, you can't do that because the applications on which you build can always have the ability to turn you off and shut you down. And that limits the ability, the innovation that can happen on top of any one protocol. So people have to, or any one company, or any one application. So people have to rebuild everything when they just want to make a tweak to Twitter. They just want to make a tweak to Facebook. You can't do that in the current setup. The problem also, though, is that Web3 projects often have centralized backends right now as well. And that is kind of a little secret of the industry, and it's nobody's fault. It's just that there hasn't been compute that's peer-to-peer that is usable and deployable yet for Web3. So for all the talk of Web3 and being decentralized, there are centralized backends and centralized APIs behind some core infrastructure of Web3. So we think soon that will be we'll move beyond that, and what we're building, Radicle Ceramic, should help alleviate and reduce those centralized risks. And so, with that, how do we build the best peer-to-peer applications? And, importantly, it doesn't all have to be on-chain, the way smart contracts are, the way we think of, especially in this kind of conference, you would think of it as being on-chain. Remember that both Arweave and IPFS, some of the most successful projects in the peer-to-peer world, their data isn't stored on-chain. The incentives and the tracking is on-chain. And so that's important to recognize that you can use this world of incentives of on-chain tracking without actually forcing everything on-chain. And so that's what Fluence, we're using the on-chain kind of tools to track and to incentivize, but we want compute to be as easy and open as possible, which makes it off-chain. And so if you look at this graphic, you can see sort of three buckets where you have centralized computing and on-chain computing, and peer-to-peer is in the middle. And there's no middleman, and there's no default redundancy, but you can obviously build it in, and it's verifiable. You can plug consensus if you want, and it's cheap and fast. And so it actually provides really the perfect trade-off, we think, between centralized and on-chain. And so what makes up the computing? It's the network, it's the language, and those allow a code creator economy. And so, discussing, the key piece of this here is the language Aqua. And so I talked about Fluence as being a peer-to-peer compute protocol. It also has attached to it, and a core piece of it is a language which allows the easy composition of native peer-to-peer applications. It's the only language which does this, that abstracts out a lot of very complex peer-to-peer code and peer-to-peer architecture, so that you don't have to write the peer discovery, for example. This Aqua takes care of all of that. And so we think that you can't have a true peer-to-peer platform without having very simple peer-to-peer application construction. And importantly, this is live today. I'm not talking about a vision of something we have in mind for 5 years from now, but right now, there's peer discovery is written, and there's we use data streams on Ceramic. There's file management using IPFS. So this is actually live and usable today. I'm not talking about a vision for years on. We have other things in our roadmap which will enhance all this, as you can see, in terms of the other side of this graph. But there's more to come. And this network runs, obviously the peer-to-peer computing network runs Aqua. And why is this important? And this gets into one other key piece of peer-to-peer, which is, think about the application construction or software construction. This graphic shows kind of the old world, where you have a version 1, a version 0, 1, and a 2. And in each of these versions, which you're accustomed to, you have users, and then you upgrade to the next version. The software author comes up with the next version, and the previous versions are out. And you're in a forced upgrade cycle. When you're in a peer-to-peer world, when your code is actually released, it's out there. And you, as the author, no longer own it. And you, as a user and as a host, can use it as long as there's demand for it, and a host can host it forever. So you actually end up divorcing authorship from ownership. Now, using Fluence, you can share monetary rewards from that in perpetuity, but this ends up with a world like this, where you can still have old versions that run as long as there are hosts available and interested and compensated for running those versions. So you're not forced into upgrade cycles. You're not forced into breaking code that you've already written or having it broken because dependencies break in new versions. You can continue to run this. And so what that means, though, is you then have no deplatforming. And so now, because this code is out there, applications out there, no longer owned by the author, you can then build on top of any of those, because the author can't shut you off anymore. And anyone can host those, and anyone can use them. So you start a world of composition where anyone can build on existing applications without fear of being cut off. And in the worst case, you're worried you're going to get cut off. You could host it yourself. And so that leads to a potential explosion in creativity, as you no longer have to innovate from the ground up, but you can innovate on top of existing infrastructure and existing code and existing applications even. And so we think this allows the code creator economy to really function, because that then allows monetization, it allows tokenization, and a huge number of uses kind of explode from there. So where are we right now? We have Aqua, and the peer-to-peer network is live and functioning. This year, we are getting ready to launch a DAO, and that will be the governance of our network. And then the compute economy, which I touched on, is going to be finished next year. So you can find us at a variety of these areas, obviously, but definitely find us at dash.fluence.dev. Fluence.network is our website. And I'm going to close with two thoughts here, which is, what kind of world do we want to live in? And do we want 3 companies controlling the internet, and with content monitored and censored by nation states, with huge barriers to building independently? This I don't think is what Tim Berners-Lee signed up for. I don't think it's the internet any of us want. And so peer-to-peer and incentivized open source is the only shot we have to not live in a world controlled by 3 or 4 companies and effectively by governments. Like, this is our only chance. So support peer-to-peer, host, contribute, follow, and empower the next wave of internet innovation. So with that, you can find us at these areas, and happy to take any questions, or just give the questions to Evgeny, Dimitri, Bernard, and Folex, which I may do as well. So thank you.
Thank you very much, Tom. That was an awesome talk. So, questions?
Thank you for this nice presentation. I'm hoping it's not a stupid question. Can you elaborate a bit more about what it means, computing? What would you intend by this, and how would it work for me as a developer? What should I push to your system, and what would I give it? What would I get back?
I mean, I guess, well, Evgeny, you can come up and address some of that, but I guess the main thing I would say is that it's any type of computation. So it's counting, it's anything that involves, think about it the other way, what's storage and what is payments, and anything that's not that is effectively computation.
So you mean that I would send a function, it would run on your system, and then I would get back the result?
Correct. And importantly, you would write it, and it might go to look up one host that it could perform in at, and then perform one function there, find another host for the next function, and travel until it was complete, and then come back to you. So instead of you writing a function that goes to one place that like AWS, and back, it actually can look up peers or hosts and find it, and then travel back in multiple places.
And therefore, I assume you guys handle different programming languages?
Yes. I mean, right now, things the answer is yes. Evgeny? So whatever compiles to WebAssembly is the current architecture.
Okay, thank you.
Virtual machines like V8 because we long-term think of supporting JavaScript. Maybe Firecracker, we need to put more research in that, but currently it's WebAssembly.
Thank you.
Sorry, there is a different questions.
That wasn't obvious. Thanks for the talk. Very good. Just to not to go too deep, but do you have some comments on how the computation is verifiably correct? Like how do I know that the answer I get back is correct?
Well, I'm definitely, that's been a topic of conversation extensively. Evgeny, do you want to, the most current thinking on that?
So the way we address, there are several layers of the verifiability. If we think of verifiability as, in terms of blockchain, like trustless computation, right? When you run some piece of computation and you want to make sure that was executed correctly, there are several ways to achieve that. First, you just trust whoever did the computation. Second, you can check via, for example, blockchain consensus, like BFT consensus. Third, you can run on trusted execution environments like TEs and trust them. And the other one is like ZK related magic, which is constrained. So by default, in Fluence network gives you flexibility. So by default, there is no mandatory verification for anything that deploys into network. But Aqua is a language for creating distributed algorithms. And for example, consensus algorithm is distributed algorithm. So you can write the consensus algorithm in Aqua and apply it to your piece of computation. This way you can enable the verification for the computation piece. And we're going to have these libraries as well, like as a part of standard Aqua library. So you would be able to have this, for example. There's also verification in terms of how to say it, when you can check that when you can see that the node executed the function you wanted to execute, but maybe you cannot check that this function was executed correctly, but you cannot be, but you can be sure that there was the right function. So there are like several layers, and the solutions to them are like there is a kind of the family of solutions, and that's not like we don't have like a full end-to-end decisions for this yet, but it's kind of the exploration space.
Yeah, just to add, one of the concepts. What's up? One of the fundamental concepts of Fluence is to reflect the real structure of the world. And in reality, there is no single solution for security, but Fluence provides many different tool sets to address different security-related aspects. So, for example, for a transition from one content addressable thing to another content addressable thing, this kind of pure function, you can try to sample some peers and repeat this computation and agree that, okay, that's okay. But for the Oracle, you cannot do this. But you have a different way to verify that everything is okay by like doing the consensus and going to the source, like to the chain. And so on. With Fluence and Aqua, you can express these constraints and these algorithms, and you can ship them and use them as libraries. Libraries both in terms of computation in Marine, in WebAssembly, and libraries in terms of this flow, this logic that goes from like Oracle to some computation, to some storage, to trigger some other function, having this kind of step function in Aqua. So if you want to know more about the approach to security, I will be there.
Yeah, we have networking after the talks, so just mind that. Who was the first? I didn't see.
So I have a question about the business model of your industry. Yesterday I was at the FileCom Meetup, and I understand that the storage provider, they have some kind of incentive with a field token. So can you explain a little bit about the tokenomics if you plan to launch such a thing?
Yes, there will be the initial Fluence coin will be a governance coin, but you will need to use Fluence to use the network ultimately. And so one of the elements I didn't get into as much, but when you're running computation, you need to create some level of relationship with whoever's running that computation or whoever's hosting that computation. And so we expect that either the Fluence for sure, but potentially limitless other coins as well, to be available to be locked for the duration of that contract and then released when it's complete. So that contract could be a minute, an hour, a month, a year, and that when the value is locked, then the provider is sure of getting the value and the user is assured of getting the service. And if it isn't complete, then it's released. But I think that is a core way the network needs to function in terms of, and so that's our number one priority, is how to build a network that's used the most and provides the most use and value to people overall. And for us, the coin is a piece of that, but it's not the driving function of it. But we also think that there'll probably be a mechanism of staking so that people providing computation will and our hosting will have to actually own a certain value that helps provide trust in them as well. Somewhat similar to IPFS, or sorry, to Filecoin. So it's a combination of those two elements that we haven't finalized, but we think both of those are relevant to a secure functioning network that provides the right incentives, and that's what we're really focused on.
Okay, thank you so much. That was really nice questions. Thank you, Tom. Let's thank you. And next, Joel. He's a CTO and co-founder of 3Box Labs, which is also a ceramic network. We changed the slides and. We can switch off the soundtrack for Joel.
Cool, thanks. Hi, everyone. Excited to be at like the only peer-to-peer event at EthCC. I think we need way more of these. We need to think much harder and deeper about like how we all work on infrastructure beyond things for like DeFi and NFTs. So excited to talk about like how we can actually scale data in Web3 and how we can use Web3 to kind of build much more scalable and usable systems. So I'm Joel, co-founder of 3Box Labs, and we're building Ceramic Network. And today I'm going to kind of get into Ceramic, but also like some of the reasons that give rise to us actually building Ceramic. So kind of what we really need for Web3 and the need that we saw is some sort of like open ecosystem for data in general. When you're building an application, you want to be able to not store your data in a centralized backend and actually like plug into an open, thriving ecosystem. And as we've kind of thought about this and built products in this space for a long time, we kind of realized that it needs to be like this open graph of information, of data in Web3. And we kind of started thinking about this as a knowledge graph of the internet, where you can represent information, you can represent various relationships and contributions and things like that. And this graph of information, of knowledge, should also be living and relational. So you can see who has like contributed what and how those contributions matter together. And from this, we can actually get to some place where we have an emergent web of trust, where not only like can you see like, oh, someone did something, but actually look at the graph of interactions to get useful information out of this graph. So one interesting use case for that is Gitcoin and not conviction, but quadratic voting, where you actually want to weigh the relations in the quadratic voting based on like something called social proximity. And the only way you can kind of get this is to have some idea of like what the different groups that are contributing look like. And the web of trust has been tried before in kind of the PGP old school crypto world, but that never really took off because they were kind of trying to introduce new social ways of interacting by like, oh, let's have a crypto party and go and sign each other's keys. Like who really wants to do that? But if you actually, all of your interactions online are signed and verifiable, you don't really need to think about building this web of trust. And I think one super interesting thing for me is like also, once we have this kind of open knowledge graph that we can see who contributed what and like make relationships kind of matter and have semantic descriptions of data, we can start to like make sense of what's actually going on in the world in a much better way, because we have verifiability, we have much more specific pieces of knowledge, and we can start to like collaborate and understand what's going on without necessarily falling into polarization and things like that. So in order to reach there, there's some things that we need to have in a network like this. And the first thing is interoperability. So we need different apps and different organizations to be able to collaborate on the same data. And this is so like, you don't get data silos. And kind of what was talked about by Tom right before, like this kind of thing where Web 2 applications can shut down access. That's really bad. And we need data to be open and shared, and we can actually share network effects. So your users are actually also my users. And we don't want to lock developers into like one specific workflow. We want them to actually be plugged into this open data ecosystem and maybe build their own custom database or something like that. But we still want the data to be composable. We want you to be able to plug in, use existing data, and not start to build new silos based on like different formats. We want to like be able to share formats and things like that. And with this, we can again like increase the rate of innovation. Another really important aspect here is that we can prove authenticity of the data and all the interactions in the network. So we want this system to be censorship resistant, of course. We want every action that happens in the system to be authenticated. And that essentially means that every action is signed by whoever the author is. We don't want a system where like I make some post to some database and then it's like up to whoever controls that database to like change the data or update the data or remove the data on their kind of whim. And we want the audit trails of like these signatures and like interactions to be verifiable. I should be able at some point later in time synchronize whatever happened and verify that that's valid. And maybe I want some timestamps and like guarantees about like when that thing happened. And if we have this kind of base layer of verifiability, all of the authors in this network can actually start to build reputation because we can see like their interactions over time. And of course, like this should be completely pseudonymous, so I don't need to like tie myself and my life to like one identifier. To be able to like change identifier use over time potentially. So this is great. Can we just do it on a blockchain? Blockchain kind of provides all of these properties, so let's just like put it on the blockchain. Well, there's some kind of problems with this. As you might know, like blockchains are really good for like financial use cases, but they don't really scale, to the web scale. And probably like will be really hard because blockchain favors something called strong consistency. And what this means is that at every kind of update to the blockchain, all nodes have to kind of agree on what has gone on. And so this is great. It allows us to prevent double spends, which is what we need for like all fun financial use cases and semi-financial use cases that we have. So great for like managing funds, DAOs, invest in things, fund public goods, like really nice stuff. We can have non-fungible tokens and all that fun. But we're always going to be like kind of limited by the block producer. So the block producer is basically the node in the network that produces the new block. And the throughput of the network is essentially limited by the size of this block. So, but there are different blockchains trying to get around this problem and just like build scalable blockchains. And there's essentially two approaches to this. One is, let's use bigger blocks. So you have like blockchains like Solana, like Arweave, like Celestia. They have different ways of providing like crypto economic incentives and new structures for how we can kind of convince ourselves that like, this big block producer is actually fine. And we just like produce really big blocks and kind of are fine with it. And still, like, we have a big block. We don't run Facebook or Twitter on like one single machine. We actually have to shard those type of like web scale systems. We can't run those on a strong consistency model. So like one machine running a big block is not going to cut it. Then we have proof of storage systems. And these provide kind of like a nicer property because I can make a transaction in something like Filecoin or CEA or Storj and tell maybe like another node in the network like, hey, I have this big file I want to store. And if I make this payment to you conditionally on you storing that file, can you please store it? So you make this agreement with one or multiple nodes in the network. And now you can actually store a big chunks of data if you made the agreement in a block. So this is great. We have like this way of having bigger throughput in the system. But the problem there is that if I have tens of millions of users, and all of these users are making updates at the same time in the system, you have like 10,000 or like millions of small updates that happen at the same time. And for every new piece of data that you put into a proof of storage system, you actually need a transaction into the block. So you're actually limited by the size of the block producer anyway. You're limited by the size of the block. You could kind of get around this by having like a centralized coordinator that just like aggregates a bunch of stuff and puts it into like a big blob and makes a deal for you. But that kind of limits the trustlessness of the system. So even though we have this like big throughput, we still can't have like massive parallel data production happening. So the question we should ask ourselves is, can we build a decentralized peer-to-peer network that is eventually consistent? So we can have this kind of massive parallel data production. And yeah, I think we can do that if we have all the event logs be verifiable, have verifiable audit trails, and essentially be completely independent. And can we do this while actually maintaining the composability? So what's really nice about blockchains is that I can have a smart contract, can build another smart contract that kind of works together with the first smart contract, which is really nice. But can I have a system like that where you build an application and you have some sort of data model? I want to actually build an application that uses your data model, but I want to use some other kind of structure for my data as well. So I can kind of read your data and also use my data as well in the system. So can we have that sort of like composability, but for data in this kind of non-completely blockchain system? And finally, we want the data to be non-financial, or like this system should at least deal with non-financial data, because for the financial use case, we actually need blockchains. So that this data kind of essentially becomes soul-bound because it's tied to like one particular identifier in the system. There's no way to like trade purely data. And so I'm actually going to introduce something that we've been working on for the last few months at Ceramic. And this is kind of like a separation of the stack where, and this is actually something that we will be releasing a developer preview soon. But let's dive in and dissect this. So at the base layer, we have event streams. And these event streams are kind of pure event streams that just like allows users to individually post events to kind of user-owned event streams. At the layer above, we have an indexing layer that creates databases. And in this system, you kind of observe what's going on in the event streams and produce a database. And on top of this, we just like provide a nice-to-use GraphQL API. And this whole system we're actually calling composability. So composability is basically a database built on top of the Ceramic event streaming layer. So let's start with the event streaming layer, kind of the base layer of Ceramic. So event streams are independently verifiable. They're made up of signed events and of events that kind of prove that a certain event was included into the blockchain at a certain point in time. We have authentication using the DID standard, which actually got accepted like an official W3C standard like yesterday, which is kind of nice. And the system we've been working on actually allows you to authenticate to Ceramic using like any blockchain wallet. So you can use like MetaMask, you can use blockchains from like the Solana ecosystem, from Polkadot, like whatever. Like you can actually extend this authentication system to work for like any blockchain system. And the event streams themselves are synchronized using a peer-to-peer network. So there's no like centralized point of failure if there's like multiple people actually running nodes that backs up these event streams. And by the nature of like the data being signed by your key or a session key permission by your main kind of maybe like Ethereum account, the data is all tied to your address. So all data is kind of soul-bound. There's no way to like transfer data in the system, which kind of wouldn't make sense anyway. And an additional thing that we're working on kind of mid to longer term with Ceramic is actually an incentivization system that guarantees like data availability of event streams, but not data availability in the sense of what you need for blockchains where you want like strong consistency for the data to be available, but rather like eventual consistency for all of the event streams to be available, but not at this in this sequenced block method that blockchain needs. So the event stream roughly looks like this. This is like an event stream of a single user. So the user starts by creating a genesis event, which is just like a simple event that might describe some metadata about the stream. Then they can create signed events that just like include some data and contains a pointer back to the previous event. And so you can just like keep appending the event log with these signature signed events. And so you can imagine like this event log could represent really anything, but you could have like it represent just like creating, updating, and deleting documents, for example. Or in theory, you could use it for like, I took this input and ran some computation, and this is the output. Ceramic at this kind of event streaming layer is really agnostic as to what you put into the event stream. And the other key important thing here is you can see that there is a, we have a Ethereum here, for example, and there's an anchor event. So here, basically what's happening is the hash of the previous event is included into a transaction that goes on Ethereum. This essentially provides a way of doing timestamps. And of course, like if you needed to do this for all events, for all streams, it would be very expensive to make a lot of transactions. So what we can actually do is just take a bunch of events from a bunch of different streams, build a Merkle tree, and put the root of that Merkle tree, or really like any sort of vector commitment, put that on chain. So now you can have a proof for any individual stream that you're synchronizing, that this particular event was included at this point in time, and you can just like store the data of the Merkle witness to not have to care about all of the other streams in the network. So I can like independently verify any singular stream in Ceramic without having to care about any of the other streams in the network. And so going one layer up, we have the database layer. So really on top of these event streams, you could build any sort of indexes from these events, and you can really like specialize for particular use cases. So for example, a database could be like completely global, an index like all of the users or data, or like all of kind of the different sorts of data in the network. Or you can make them index like subsets of data, maybe like particular models or like schemas in the network, or maybe like particular subset of users. Maybe you have like a very local peer-to-peer app that only wants to like index 3 users or something like that. But the idea is that you can have this flexibility in how you choose to consume the event. And so finally, this kind of can give you a flexible consistency model. So you can, what we're doing with composDB is actually allowing anyone to spin up a node and just like index whatever they want and actually store that index locally in their node. But you can imagine a system that kind of has some consensus mechanism that chooses to like, hey, we want to build an index and have consensus over that index so we can like know and that we're in the same page. So in composDB, as I mentioned, it's a local index or node-centric index. And in this composDB system, there is a model for data. So this is essentially a semantic data model. It has a JSON schema that defines kind of the structure of documents that are written to the database. And a node operator can essentially choose, like, hey, I want to index model A, model B, but not model C. And then essentially you can think of it like when you start this node, you can synchronize the history. And instead of like in Bitcoin or Ethereum, you synchronize all of the history through time. You essentially only synchronize the pieces of the data that you care about. And so finally, eventually you'll be able to query data across linked models. So you can actually link models together, see like, hey, this is my proposals, and this is comments for proposals. For this proposal, give me all the comments. And so that can kind of allow us to build like really feature-rich applications, which has been really hard in the Web3 space so far, because like any type of writes that we would need to do has needed to go into the blockchain, which is like very expensive. So I'll talk a little bit more about the data models that's used inside of composDB. So the data model is essentially a JSON schema plus some metadata information, and that's it. And then any user can write to this model, but any user actually writes to their own event stream So there's no need to kind of have some access control or anything like that of like which users are allowed to write, but instead your node can choose to index like a subset of users. So you can have this kind of open write access to that data model and potentially like restrict who you're indexing in the future if you want. These data models can be easily created using the GraphQL schema definition language, which is kind of like a very easy way of like defining just like a schema. For some reason, emojis doesn't work on this computer, so I'm sad. But yeah, of course, then you can make like GraphQL queries over the data. And the nice thing about these data models is that they're discoverable and they're reusable and they're composable. So if there's like 5 people here building different apps, I could pull in all of those 5 different models into my application and just use them and already have access to like all of the data of your users if of course the users consent to use my application. So what this would look like to actually defining this model, it would look something like this. I don't know how viewable this is, hopefully somewhat viewable. Let me know if, I don't know if you can zoom in here. Essentially here we have a proposal. So think of this as like a proposal to a DAO. This is a very simplistic model. So we have a text, which is like, you know, the text of the proposal. And then we have another model below, which is a comment. And here we also have a text. And also, by the way, the author property here is basically just like a contextual property that just pulls the account, the ID of whoever was like authored a particular proposal or comment. Then in the comment, we have a proposal ID. And there we basically just reference the ID of a particular proposal. And so this is essentially what, not yet, but will enable us to, in Ceramic, just make a query for a proposal and giving all the comments in the same query. As you can see, like this is fairly easy to just like write one of these, and what you will be able to do, like once there's like a set of models available in the network, is kind of just like, hey, I want this proposal and comments already exist, and I want to use that in my DAO as well. But now I also want to have like likes or upvotes and downvotes for comments or proposals or something like that. So it's easy to like extend models with like new properties or new things in this way. So I think I went through like mostly like what composability is and what we're about to release a developer preview of soon. So what are some of the use cases? Well, any sort of things about like online communities is interesting and fun. Like I don't think we should try to, some people are like copying Twitter, copying like different social networks from Web 2 into Web 3. I don't think that's the right approach. We should think about new ways to creating communities in Web 3 that are more kind of native to our way of being and interacting. So let's come up with new ways of building online communities. DAO tooling, I think there's a lot of like open opportunity around DAO tooling, and some of the kind of DAO tooling systems I see right now, they build just like systems that just store data on a centralized server that just enable DAO collaborators to do stuff. But then the data is locked into that particular platform. It's not really composable. We want that sort of thing to be like composable and reusable across the ecosystem. One use case that I'm like extremely excited about is scientific knowledge graphs. So once you have this way of modeling kind of graphs in a system, what becomes really interesting, like can we actually model kind of scientific like logic and discussions in this? So you could put for example, put like what's a research question, what's a claim, what's some evidence, how do they relate to each other, and then use that as a basis for our scientific and other sort of like discussions, maybe like even base policy based on like actual scientific proven or like proven, but like based on real like scientific discourse and how like you can kind of model propositions inside of this. So like there's a lot of like potential in that. And finally, like really exciting to think about once you have these knowledge graph, these DAO collaboration, online communities, since all the data is verifiable in Ceramic, you can see which accounts did what and how they interacted, you can actually just look at these event logs and compute some kind of, okay, this is weighted map of like how people contributed, and then do like a communal kind of retroactive funding to people based on how they interacted. So I think like that sort of thing is really interesting to explore for new projects, like thinking about like reputation and things like that. All right, so if you're interested in all of this, we're going to have an updated documentation soonish on our developer website. And if you want to chat to us about this, you can join our Discord. Thank you very much.
Thank you so much, Joel. Thank you. Questions?
Thanks for this presentation. It's really cool to see that. How would you relate that to Tim Berners-Lee's Solid initiative? It looks very similar in terms of philosophy. So what link would you make with it?
Yeah, so I don't think I can like fully answer the question because I don't know the Solid approach like super deeply. But from my perspective on it, they have this concept of pods where you can choose to run your own pod that stores your data, or you can have some service provider storing your data. And that's kind of fine for technical users to like run their own pods. For most users, probably not going to want to run their pod, so they will rely on some service provider. And then they're kind of at the whim of that service provider. I think it can work, but I'm kind of worried for that sort of solutions. There are similar solutions as well, like a few different ones. That I'm worried that like you'll end up with network effects with like one big company like Google or Microsoft or whatever that runs a lot of those nodes, and a lot of users just get locked into that system, and there's like capture of that. Whereas in Ceramic, we're focused on like building this open network where and that will eventually have incentives to just like keep the data available in a decentralized way. And I think that's the main differentiator for us, that like there's public verifiability of the changes, and the network kind of is decentralized, so there's no particular party that like has control over that data.
Okay, thanks.
Okay. More questions? Okay, sorry. Cannot see you from there.
Could you maybe explain what your incentive mechanism for data availability looks like? I think you called it eventual data availability guarantees.
Yeah, so I mean, this is something that we're still kind of working on and doing research on. I think the main difference is that we want to have an incentive that makes sure that there are nodes in the network that continually keeps data available, but not necessarily like, oh, at this point in time, all of this data in a particular block is available. So it's probably going to look like some sort of like sampling mechanism that just like across the set of streams in the network that have kind of paid for to be sampled, there will be nodes that actually be incentivized to sample, make sure that data is available, and that the kind of progression of the event streams is not halted. So like you actually have an incentive to store new events rather than just like only store like a certain subset of events in a stream. I hope I can share more of this soon. We have like some internal working papers, but it's not ready to be shared like publicly yet.
Okay.
Happy to also like chat one-on-one, might be easier.
Yeah, sure. Thanks.
More questions? Okay, let's leave the rest to the networking. Thank you so much, Joel.
Great, thank you.
Thank you. I used the wrong mic. Okay, and next up we have Alexis, co-founder of Radicle, a really cool platform. He will tell you now.
Okay.
Yeah, okay.
Hello. Okay. Cool. Hey. All right, so this is going to be a bit of a shorter presentation, as I thought I was going to be able to do a demo, but this isn't my computer.
You can do the demo if you want.
No, I can't on this computer, but
okay.
Maybe I'll show the website. Okay. Anyway. Yeah, so Radicle is essentially a peer-to-peer code collaboration network. But today I'm going to talk a little bit more about the foundations on which it's built. and on which any kind of collaborative network can be built. So, so there's kind of three problems that we're tackling with Radicle, and which I think a lot of peer-to-peer networks need to tackle in some way. The first one is how to reconcile divergent histories. So if users are working on a document from their laptop and eventually they go online or they go offline, there may be conflicts. So someone changes something from A to B and someone changes it from A to C, and then there needs to be an algorithm that reconciles that and decides whether it should be B or C in the end, right? And so a common way to solve that is CRDTs, or conflict-free replicated data structures, but there's other ways. So for example, for source code, Git has a way to resolve conflicts for a lot of types of changes. It has merge algorithms. And when it can't do that, it asks the user to resolve that conflict manually. Now, the second thing is basically how do we get data to and from users? So how do we transfer? How do we replicate? How do we create redundancy in the network? So that's generally the kind of the problem of replication. And since we've been building Radicle on top of Git, given that it's a great fit for source code, we're using a lot of Git's replication technology, and I'll go in it a little bit more. And the final thing is identity, and for this it's really the idea of like, well, how do I identify a certain document or user as being original or as just being who we think they are, essentially. This is something that Git doesn't solve. So you take two Git repositories, you can look at the source code, you can say, oh, the hashes match, but this isn't an identity, a solution to identity. It could be two repos that happen to be at the same change from different users, and they intend them to diverge. They could be forks of each other, etc. So Git really solves the replication problem. It solves some of the merging or the conflict problem, and it doesn't solve the identity problem. And so we had to build Radicle, we had to find solutions to these. So I'm going to go through them, through the three, and explain kind of what we're doing. So for merging divergent histories, so we're using CRDTs, which is a pretty common technology that's been around for a while. We're calling them collaborative objects. So the types of CRDTs we're using, and they're essentially based on auto-merge, which is a fairly new type of CRDT that is extensible and that allows you to basically encode most kinds of operations that you would want to encode, whether it's like appending to a list or mutating something or whatever. And one of the really interesting things we're doing, because we're essentially using Git as a database, is that we're encoding the CRDT into the Git commit graph. And it's not the commit graph of your source code, it's kind of a hidden commit graph, but it's essentially each, and there's a little diagram of that here, essentially each event in the CRDT, like commenting on an issue, so if you have something like issues or pull requests, you'll have a lot of events. All of these events are represented by a commit in a Git commit graph. And as you know, well, if you use Git, you'll know that commits have parent commits, and this perfectly represents a graph of events in a decentralized system, essentially. Now, instead of using Git's merge algorithms to reconcile this into a linear history, we use our own algorithms based on auto-merge to essentially render this into a timeline, for example. And there's a bunch of things we can do there, like validation and filtering and things like that. Then there's replication. So with replication, as I said, we're using Git's basic replication protocol, which is super nice and efficient for text. It's also pretty good for binary, but essentially it's very efficient because it's interactive. So as opposed to something like IPFS, which is great for like static files, With Git replication, you have a little interactive step before the replication happens where the two nodes or the two peers sort of say, hey, I have this, but I don't have that. And so the peer that has the data will generate pack files, which is essentially compressed archives with all of the data that the other peer doesn't have, nothing more, and send that over. And so we take advantage of that for replication, which for us is not just source code, it's also things like issues, PRs, social artifacts, whatever you want. In terms of the network architecture, this is kind of something we're still working on, but it's a little bit more like something like Bitcoin and Ethereum rather than something like Scuttlebutt or DAT, if you know about those. And by that I mean that users don't usually run Bitcoin and Ethereum nodes on their laptops, right? They'll have some kind of server somewhere if they're running them, and the servers are going to talk to each other. But your laptop is effectively going to work as a client to those servers. It's not going to act as a peer exactly. And so we're taking that same approach, which means that the seed nodes, which is what we call them, interact with each other on a peer basis, peer-to-peer basis, but client machines interact on a client-server basis with the peers, with the seed nodes. In terms of storage, as I said, we're using Git, and I'm really using Git as a database. We're using some of Git's features to essentially namespace different code repositories inside the same physical location on your hard drive. Both the clients and the servers, or both your laptop and a seed node, have the same structure and the same database. So that allows us to use Git replication. And we call this a monorepo colloquially because it's kind of like a huge repo with lots of other repos inside. And this is, of course, hidden from the user. The user works as usual with a working copy, and they push and pull. And this is just kind of the implementation, the way we're storing things. And yeah, and in terms of the kind of transport, we're using Quick. So the kind of, well, it was going to be HTTP3 at some point, but it's a UDP-based protocol that is pretty efficient. You can kind of multiplex it with streams and stuff like that. And within Quick, we use the Git protocol, but the Quick transport allows us to have multiple streams running at the same time, which is quite handy. And then finally, identity, which is a complex one. I think a lot of different peer-to-peer projects are trying to solve this at the moment, and there isn't really like so Ceramic has a solution for this as well. There isn't really something that has been fully accepted yet. So when we started developing this, we were thinking of the idea of essentially a chain of trust. So essentially, when a project is created, an identity for it is created, and when that identity is updated, there needs to be a sort of proof of that update, and whoever is trusted in the original project is trusted to make that change. And they can also confer trust to a different group of people. So here in this little example on the right, at the bottom is kind of like the first version of the identity of a project or of a person. So it uses the same system for like projects, like code repositories, and for people. So in the beginning, let's say there's you're A, so you created the project, and you're in that list of sort of signers, let's say. We call them delegates. And then you say, okay, I'm going to add B, and now B can also sign on behalf of this project, right? Or it can also sign for this project as well as me. And then eventually, A and B, we agree that I'm going to be out, I'm leaving the project, and I'm going to add C to replace myself, right? We're going to sign on that. And so that's kind of how you create this chain, right? And by the end, A is no longer part of the delegates or the trustees. You just have C and D. But you can always trace back any project state back to the original founder of the project, essentially, which in this case is A. And this works the same for identities, and this is how we deal with the multi-device problem. So this is how we allow a user to have a laptop and a mobile phone and the desktop, and it's always them, and we don't have this kind of issue with multiple devices. Of course, it uses public key crypto, and again, when we think about storing this here, there's since identities are they're not really a DAG. They're more linear, but we still use the Git commits to represent individual versions of an identity. It's again a disjoint branch, so it's not your source code commits. It's a separate hidden set of commits that are part of the Git object database. And yeah, and just a little bit about the way this works, the kind of different pieces that users interact with. So we have a CLI now. Maybe I can show a little screenshot or something, which is how users are onboarded. So you create your identity on there, you create your keys, etc. You create projects through that. You have your local, monorepo, as we call it, which is stored on your device. The CLI can interact with the web. It can also interact with a seed node via the replication mechanism. And then seed nodes are run by, so we run a few at the moment, but any user can run their own seed node. And eventually we're thinking of incentivizing these. And seed nodes have an HTTP API to be interacted with by like a web client or something like that. Radicle link, which is our peer-to-peer replication protocol. And then they have a Git server, which is kind of a bridge, which allows users to use just vanilla Git commands, so they don't have to always install our tools for things to work. And that's about it. So no demo this time. You can try it out already. What exists today is essentially all the identity stuff. The CRDT stuff is kind of built at the protocol level, but we're still working on things like PRs and issues and discussions and things like that, although that's coming very soon. And of course, things like hosting and all of that are available. Maybe if I can I switch this over to the website just to show? Yeah, just to kind of show the onboarding flow, I think. For some, yeah, that's perfect. Okay. Is this gonna switch? Switch through? Okay, just a moment. You can also just go on the website. Oh, yeah. All right, well, I mean,
restart this
Can
you restart this page?
Yeah, sure.
Can you close?
Yeah.
You have to close?
Just copy paste it.
No, I don't want to do that. You are another desktop. Start on this desktop.
Yeah, sure. Sorry. Okay.
Think about your questions while we're setting up.
Okay. We're getting there. Macs are complicated. Okay. So I'll just paste this here. Great. So this is just kind of the get started page. I just wanted to go super briefly into some of the flows. Oh, it's very small. Hold on. Second. No, wrong direction. Wrong direction. Even wronger direction. Oh, here we go. Let's make it. Yeah. Okay. Yeah. So like a user would basically, when they want to use Radicle, they would install the rad command line tool. They would run rad auth, which authenticates them, or it creates a new identity the first time you run it. Username, passphrase, which protects the key pair. a couple of other things. You'll get a peer ID, which is per device, and then you'll get a URN, which is across devices. So it's your user ID kind of. And then you will run something like radinit to turn a Git repository into a Radicle project, which doesn't change anything in the repository itself, really. I mean, it adds a remote, but it doesn't really do much there. But it creates this identity, which I showed with the version. So it creates a first version of that is sort of content addressed to the commit of your project. And then you can push. At the moment, we have a couple seeds running, but eventually this is kind of all going to be abstracted, and it'll replicate across seeds. Yeah, this is the kind of syncing and the pushing process, and it'll give you a link to where you can find your project. Yeah, and rad clone is kind of the reverse. It'll clone a Git repository, but in a way that is project aware, essentially. And that's it. That's what it. Thanks.
Thank you so much, Alexis. So, questions from the survivors.
Hey man, great talk, thanks a lot. I wanted to ask, do you have already end-to-end encryption on the network? And I guess, can I create right now a private repository on Radicle?
Yeah, a lot of people are asking for this. The answer is no. This is something that is possible, that we've been talking about for a long time. At the moment, we're kind of like optimizing for the open source use case, which is public by default, essentially. There's one sort of option that I wouldn't necessarily recommend, but it's a potential path forward, which is that you can kind of choose where you want your data to be replicated, and if you don't replicate it to a public node, it's essentially private, right? But the peer-to-peer communication is encrypted via TLS, right? But the data at rest is not encrypted, so you need to trust the node with your data if it's private, right? But yeah, it's something we're looking into for the future.
Thanks.
Maybe another thing on that. There is maybe a problem with incentives in terms of replicating encrypted data. So that's a problem we would have to solve also, because a node is not going to want to host a bunch of garbage data essentially for free. So something to think about. Anything else?
Thank you. Mm-hmm.
Thank you. We are animating a community of contributors. We are an open source solution, and we have developers contributing to our solution. We know you guys implemented something called drips. It's been recommended to us. Could you elaborate a bit more about how it works? We are thinking about using it to contribute back to the contributors to our solution. So could you elaborate a bit more about how it works and if we could actually implement it?
Sure. Yeah. So at the moment, Drips is kind of like a separate system from what I showed. So it's based on Ethereum, and it doesn't use the Radicle identities and stuff like that yet. It's kind of completely separate. But yeah, I mean, essentially there's a protocol layer which it's a set of smart contracts, and I think we're able to stream any ERC20 token yet. So Ellie here knows a bit more, so I might. Yeah, we have this hub essentially that creates a sort of network of people who can drip and people who can receive drips. And this is kind of the innovation, I would say, because if you're just trying to stream like from one person to another, that's very easy to write a contract to do that. Whereas with drips, what's interesting is that you can efficiently stream to hundreds of people, as well as receive streams from hundreds of people. So for things like crowdfunding and things like that, it's much more interesting. And there's a mechanism called splits, which I think is also super interesting, which allows you to, when you receive a drip, to split it to third parties, to anyone you want to receive a share of that money or that token.
Wait, there is a Radicle team here today.
Yes, so if I can add one thing, I believe that probably the person that recommended you drips was referring to, was probably had in mind the last feature that Alex mentioned, which is the splitting component. What's cool about that is that you can do this programmatically. So you can actually have a little configuration, a smart contract on Ethereum that says that if money hits that smart contract, split them based on that rule set. And we've seen some cool use case with that. For instance, when we launched that thing, we had the Solidity language team said that like, hey, this is us, the Solidity language. We are 100% founded from the Ethereum Foundation. But if you want to support us for our open source work, we're going to programmatically splitting 100% of those funds with people in the community that have made our work happen. So that's one of the unique things that you could do with Drips. And the website is drips.network if you want to check it out. Yeah.
Thank you.
Hey, so there's Git and then there's GitHub and GitLab and like the kind of features that they've like added over the years. So and you mentioned just now like adding comments. So my question is about the mid to long-term scope. If these kind of things like CI, etc., if that should be part of Radicle itself or of tooling that is external to it. What you envision, like what is actually part of it or what's external?
Yeah, cool. Yeah, so obviously things like PRs and issues and commenting should be part of Radicle because there needs to be a solution for merging histories and essentially owning your own data, right? Like you want to have your comments on your machine. You don't want anyone to take that away from you. You want to be able to work offline, etc. For CI/CD, I think it's a little bit different. We don't really intend right now to build our own like Travis or GitHub Actions type thing, like our own CI runner. But we do intend to integrate with an open source solution. And the way that would work, I think, is the main challenge or the main thing to think about is getting the results back from CI, right? So let's say so today you could set something up where essentially you say, okay, I have a CI runner somewhere. I'm going to pull a Git repository every 10 seconds or every minute for changes. And since Radicle projects or seed nodes expose a Git repository as an interface, you can do that, right? And whenever I have changes, I'm going to build them, right? So the CI for this can already be built today. The question is, how do you get the results out of that back into the user interface, right? So that's one thing we need to figure out. Like either on our web UI, we need to integrate these results. So like the little checks, right? The check marks on your PR and stuff like that, or on the CLI. And then the second thing that's a little bit more complicated, perhaps, is trustless CI. Like, do we want to have a solution for something trustless where you can say, hey, I'm just, it's maybe going a little bit more towards something like Fluence where you're saying, I don't know where this is going to be run, but I want to run a CI job and I don't want to trust anyone because I don't really know who to trust, but I want the results to be verified in some kind of way. That's obviously much more complicated. There are some potential solutions we've talked about, although they are expensive. They're inefficient, but they're possible. And one potential example or area of research is doing something like a BFT build where you have a random sample of like 3 nodes that that run your CI, and then you have a commit reveal scheme, and you kind of see like, okay, they've all agreed on the CI results, therefore it's trusted, or like it's sort of verified. Or oops, one of the nodes has a different CI result, and therefore it needs to be rerun because it looks like someone is lying, essentially, right? That's complicated. It relies on like deterministic builds and a bunch of other things like that, or deterministic tests. But it's a potential area of research. Yeah.
Cool. Thanks.
Thanks for the question.
Hi, thanks. Awesome, really happy to see the progress. Just to very small technical question, not so interesting. Like, are you syncing between these seed nodes?
Right. So not yet at the moment.
But you're working on this.
Yeah. So we have the tech to do that. It's not super reliable right now, so we have it off by default. But yeah, essentially that's kind of the goal, is to sync between seed nodes. There's not really at the moment we're not really looking to sync between, as I said, like user laptops and seed nodes, due to like things like NAT traversal and all the complexity there. So that's kind of more like, far future. But yeah, between seed nodes is the goal. Yeah.
But I can turn it on if I want to play with that. That's awesome.
Yeah.
Can I have the mic? Thank you. Okay, thank you so much. Thank you, Alexis. Yes, there is a Radicle team. If you have more questions, please. Yeah, thank you, speakers. Thank you, teams. Today, I think we had 3 awesome talks and have now more information about all the projects and waiting for the more updates and releases. And thank you all. Let's enjoy now some snacks and drinks. We have some beer, juices, etc. Please network and enjoy the evening. Thank you so much. Oh, and please grab a t-shirt and a hat as a souvenir.